Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 24, Design of Binary Subtractors. This lecture is a continuation to Chapter 5, which is Arithmetic Network Design for the course Digital Logic Design. The course may be called Digital Electronics or Digital Systems or the Switching Theory, to name few of the names of this course. The next slide is a disclaimer for you to read. There are many references in digital logic design. I cite 3 references here for you. In Chapter 5, we talked in the previous lecture, design of binary adders. Today we will talk about design of binary subtractors. Then we'll cover design of magnitude comparators, design of binary multipliers, and design of ALU, which stands for Arithmetic and Logical Unit. Then we will cover a VHDL design section, which is section 4. What's a subtractor? A subtractor, it's a device, a combinational network that subtracts 2 numbers, a minus b, where a is the minute and b is the subtrahend, to produce the output, which is the difference between a and b. And the simplest subtractor is a half subtractor. A half subtractor subtracts 2 one-bit numbers, a minus b, where a is the minute and b is the subtrahend, to produce a 1-bit difference d and a 1-bit borrow out, which is b out. But the half subtractor is unable to take into account a borrow in from a previous stage. So if you look at the block diagram of a half subtractor shown in figure A, we have 2 one-bit numbers a and b, and the outcome is the difference d and the borrow out b out. Then the truth table is quite simple. We have a, b, the inputs, and d and b out are the output. Okay, and the combinations of 2-bit numbers 0, 0, 0, 1, 1, 0, 1, 1. Then we say 0 minus 0, the result is 0, and the borrow is 0, because 0 minus 0 is 0, and we did not borrow anything, so it is 0. 0 minus 1, we cannot do it, so we have to borrow 1. If we borrow 1, it will be 1, 0 minus 1, and 1, 0 is 2 decimal minus 1, which is 1. The difference will be 1 binary. So 1, 0 minus 1 will be the difference 1 and the borrow 1. Then 1 minus 0, if a is 1 and b is 0, 1 minus 0 is 1 and the borrow is 0. And 1 minus 1, the result is 0 and the borrow is 0. So we will end up with this truth table. From the truth table, we can find the equations, the switching equations for d and b out. Clearly, d will be a prime b or a b prime, because it is really m1, minterm 1, or minterm 2, because I have 1 here and 1 here. So it is a prime b, we read it from the table, or a b prime, whenever I have d is equals to 1. Okay, so this is d. But a prime b or a b prime, it's an exclusive OR, so it is a exclusive OR b. How about b out? B out, we have only 1 here, so b out can be represented by 1 minterm, which is a prime b. B out will be a prime b. So clearly, we can implement this with 3 gates. We need 1 2-input exclusive OR to get d, and we need an inverter to invert a, so we'll get a prime, and an AND gate, okay, to AND a prime with b, so this will be b out. We know that this is the famous 4 two-input NAND gate can represent an exclusive OR, okay, and by simple circuit manipulation, we know that the output here of this NAND gate will be A prime B all prime, so we need one inverter to get a B out, and the exclusive OR will give me the output D. So in 5 NAND gate circuit, 5 two-input NAND gate circuit, we can implement D and B out, and D and B out. So this is the half subtractor. It is super easy. It is very simple. We have two 1-bit numbers, and we get the difference D and the borrow out, which is B out. And we defined there's no simplifications to those equations, so we don't need K-maps or Boolean algebra at all. And we can define D and B out, and we can implement them simply, either with an exclusive OR, inverter, and AND gate, or with 5 two-input NAND gates. The next slide will talk about a full subtractor. A full subtractor subtracts together two 1-bit numbers and a borrow n bit as well. So we'll perform the operation A minus B minus Bn. Now, again, we have in A, the blank diagram, we have A and B, the two 1-bit numbers, and we have Bn, which is the third bit, and the full subtractor, and the output, which be the difference D, and the borrow out, which is B out. So again, we need a truth table with all the possibilities for A, B, and Bn from 0, 0, 0 to 1, 1, 1. And we have 2 to the power 3, so we have 8 different possibilities. And we perform the subtraction, A minus B minus Bn. And by doing that, we will come with this table, okay? So D will be 0, 1, 1, 0, 1, 0, 0, 1, and B out will be 0, 1, 1, 1, 0, 0, 0, 1, okay? As an example, actually, if we say the last one, 1 minus 1 is 0. Minus 1, we cannot do it, so we have to borrow 1. If we borrow 1, we get 1, 0, minus 1. So you'll get the difference 1, and the borrow out is 1, the last line. And you can check all the lines similarly. So once we have those equations, we can define D as a sum of minterms. If you look here, D is 1 at M1, M2, not M3, and M4, not M5, not M6, and M7. So this is D. With simple Boolean manipulation, we can define D as A exclusive OR B exclusive OR Bn. So A exclusive OR B exclusive OR Bn will be the difference D. B out, the same thing. The sum of minterms 1, 2, 3, and minterm 7. Okay, and by simple Boolean algebra manipulation, we'll find B out is A prime B or the exclusive NOR of A and B. So A exclusive NOR B. And by doing this, we defined D and B out. We can implement them. We need 3 exclusive ORs we need 2 exclusive OR to implement D, because D is A exclusive OR B exclusive OR Bn, and we need some gates. We have the exclusive OR of A exclusive OR B, just we need to invert it. We don't have to use another exclusive NOR. We take the output of the exclusive, we invert it. As you see, this is the inverter. Okay, so we get basically exclusive NOR. Then we OR it with A prime B, and this is, we will give me a B out. And we can implement this also with a 9 two-input NAND gates, where I can get the difference D. This is not S, this is D. Okay, and this signal here, which is A prime, B prime, all prime, taken here. I didn't put the line to avoid confusion for the drawing. So this signal here, and this S has to be changed to D. This is the difference, D. Because if you cascade two exclusive OR, you will get D, which is A exclusive OR B exclusive OR Bn. Okay, so you have A, B, this is the output exclusive OR. Then this output taken exclusive OR Bn, so this will give me the difference D. And B out, simply this will be represent B out, which is the output here taken along with this, those two outputs taken together to give me a B out. And you can verify this. So the only typo here, S has to be changed to D. S has to be changed to D. So this is the full subtractor. Again, will enable me to subtract three 1-bit numbers and give me the difference D and the B out. One of the numbers is the Bn from the previous stage. So we implemented a full subtractor easily with gates and with all NAND gates if we want to. Now, n-bit Barrow-Ripple subtractor, it's very similar to the n-bit carry ripple adder. The two n-bit numbers are A and B, where B is the subtrahend subtracted from A, the minuend, and the output of this module is the difference D, where D is A minus B. So here we use the first stage. We don't have borrow in from a previous stage. So if we do have, we use a full subtractor. We use the half subtractor, followed by a full subtractor 1 to a full subtractor here. And the output will be the difference D0. Then you take the B out as a B in to the next stage, and D1, then the B out, you take it as a B in, and so on to the next stage until you get the output. So by this, you will perform n number n-bit Barrow-Ripple subtractor, and this is really, it also has a lot of delay because of the ripple effect of the Barrow that we have to feed into the successive stages until the last stage, and you have to wait for the last answer after the propagation delay being executed and the answer fully registered at the output. So this is an n-bit Barrow-Ripple subtractor. It's super easy. There is nothing fancy. And we said if we do have a borrow in from a Fourier stage, we change this block here from half subtractor to a full subtractor, which is full subtractor 0 would be. The next one is n-bit Barrow-Ripple subtractor using full adders. And the concept here is very simple. When I say the difference D is A minus B, it is A plus minus B between parentheses. Or it is A plus the 2's complement of B. Or the 2's complement is the 1's complement plus 1. So it is A plus the 1's complement of B plus 1. Now how we do that? To get the 1's complement, we need inverters. So every B0 will take into an inverter, B1 will be taken to an inverter, and Bn to get the 1's complement. And C in 0, the first input will be 1, because we will add 1 to the 1's complement to A, will end up with the difference as an output. Okay, so this is subtraction by using the 1's complement addition method, or it could be viewed as the 2's complement addition method. So we do have Cn 0 is 1, and we complemented the B's to get the 1's complement. The 1's complement plus 1 is the 2's complement plus A will give me the difference D. So the output will be D0, D1, Dn minus 1, and C out n minus 1, which is the overflow, the final overflow, which is at the output bit, which is the most significant bit of the answer. And this could be replaced with much better circuit. To avoid the ripple effect, we will use, this also has a ripple adder subtractor, but the following one, we can avoid the ripple effect with using an integrated circuit adder. The ripple adder subtractor, this is the same concept by using the 2's complement method, but the circuit can be implemented to perform addition and subtraction at the same time. So rather than using NAND gates, we are going to use exclusive OR. So if C is 0 in this circuit, the circuit will operate as an adder. Why? If C is 0, 0 exclusive OR B0, you will get B0. 0 exclusive OR B1, you will get B1. 0 exclusive OR Bn-1, you will get Bn-1. Taken to a full adder with A0, A1 to A-1, we'll get the sum S0, S1, Sn-1, and the carry out. If Cn0 is 1, okay, we'll get 1 exclusive OR B0, you will get B0 prime. So this will perform the 1's complement. 1 exclusive OR B1 will be B1 prime, and so on and so forth. So you will get the 1's complement here, plus 1, we'll get the 2's complement. Okay, the 2's complement of B's plus A's will give me the difference D's, D0, D1. So this circuit is very similar to the previous circuit, except we replaced the NAND gates, the inverters with exclusive OR, and Cn0 either 0 or 1. And this will enable me to combine both functions in one circuit, which is a ripple adder subtractor. Beautiful circuit. Now, enough of this. If we like to avoid, if we use a chip which is not a ripple adder chip, like the 74LS83, with a multiplexer, which is the 74LS157, the concept here is very similar to the previous circuit. The multiplexer will pick up either the B's or the B nuts. It means either the B's or the complements with the B's. And based on Cn0n, if the Cn0n is 0, the multiplexer will pick up the B's. Okay? And if we pick up the B's, this will be a normal adder. So the output here from the multiplexer will be B0, B1, B2, B3, and this will perform addition, and the output will be S0, S1, S2, S3, and C out. If Cn0 is 1, the select line, the multiplexer will pick up the B primes. So B0 prime, the B1 prime, B2 prime, B3 prime at the output, to be added, which is the 1's complement, to be added with the A's, to be added with 1 as a carry in to the 4-bit adder, and the output will be the difference, D0, D1, D2, D3, and the carry, the Barrow out, and the Barrow final Barrow out, which will be the most significant bit of the answer. So this is by using a 4-bit adder and a multiplexer, we can design simply a 4-bit adder subtractor. Okay, and since this chip is a good adder, a fast adder, so we'll get a very fast subtractor. So this is a great substitution to any of the previous circuits that we looked at previously. And this is the conclusion of subtractors, binary subtractors, design of binary subtractors. And I would like to thank you very much for listening. Please subscribe. To subscribe, there's a logo at the end on this slide. The logo is like a blue circle with letter I in it. So you click on it to subscribe. And I thank you again. Hopefully to see you very soon. Sincerely, Dr. Hassan.